Improper crimping of electrical connections poses significant risks, including increased resistance, loose connections, elevated fire risk, and diminished circuit performance. Reports from electricians indicate increased resistance and heat buildup in poorly crimped Buchanan crimp caps, signaling a potential fire hazard. Some have witnessed fires initiating at the connection point due to loose or improper crimps. A 2011 study by Underwriters Laboratories, ORL, demonstrated that flawed crimping methods can generate high resistance at the connection, elevating the chances of overheating and fire incidents. The Electrical Safety Foundation International, or ESFI, has recorded instances of overcurrent protection devices, or OCPs, failing to trip due to high impedance connections resulting from ineffective crimps. Poor crimping can lead to a loose connection, resulting in increased resistance. This, in turn, can cause heat buildup and increase power consumption. Buchanan crimp caps that are not crimped correctly can loosen over time, introducing a potential arcing hazard and the risk of insulation damage. High resistance and loose connections significantly increase the probability of a fire starting at the connection point. Poorly executed crimps can diminish the conductivity of the circuit, thereby affecting its overall performance and reliability. The Buchanan Quad Indent tool is engineered to produce a 4-point crimp on the Buchanan crimp cap, which ensures a secure and effective connection. Using pliers or other tools to crimp the caps may lead to an incomplete or uneven crimp, causing the problems previously mentioned. To ensure the safety and reliability of electrical connections, it is highly recommended that electricians firstly use proper crimping tools designed for the specific type of connector being used. Secondly, follow the manufacturer's instructions for proper crimping techniques. And thirdly, inspect connections regularly for any signs of looseness or damage. The issues that can happen with electrical connections if crimps are not done correctly include firstly, increased resistance. Poor crimping can result in a loose connection with increased resistance, which can lead to heat buildup and increased power consumption. Secondly, loose connections. Improperly crimped Buchanan crimp caps can become loose over time, creating a potential arcing hazard and risk of insulation damage. Thirdly, increased fire risk. High resistance and loose connections can increase the likelihood of a fire starting at the connection point. Fourthly, diminished performance. Poorly crimped connections can reduce the conductivity of the circuit, affecting its overall performance and reliability. Focusing on proper crimping techniques with the right tools will avoid these dangers in electrical work. Electrical fires can stop because of various reasons, and one of them is high resistance in connections. High resistance in electrical connections can occur due to several factors. These factors are firstly, loose connections. When connections are not tight, the contact area between conductors is reduced, leading to increased resistance. Secondly, corrosion. Over time, corrosion can build up on the surfaces of conductors and connectors, increasing resistance. Thirdly, improper crimping or splicing. If wires are not properly crimped or spliced, the connection may be weak and have high resistance. Fourthly, damaged conductors. If conductors are damaged, such as having broken strands, the effective cross-sectional area is reduced, increasing resistance. Fifthly, dissimilar metals. Using dissimilar metals in a connection can cause galvanic corrosion, leading to increased resistance. Sixthly, overheating. Excessive current flow can cause connections to overheat, which can degrade the materials and increase resistance. High resistance in a connection leads to heat generation, as electrical energy is converted into thermal energy when current flows through the resistance. This heat can ignite nearby combustible materials, leading to a fire. Additionally, high resistance can cause voltage drops affecting the performance of electrical equipment. The key to preventing fires caused by high resistance connections is to ensure that all connections are made properly, using the correct tools and techniques. Regular inspection and maintenance of electrical systems can also help identify and address potential issues before they become hazardous. Overcurrent protection devices, also known as OCPs, are critical components in electrical systems designed to protect against overcurrent conditions such as short circuits and overloads. However, there are situations where OCPs may fail to open properly, leading to potential hazards including fires. Several factors can contribute to this failure, including firstly, device malfunction. The OCPD itself may be defective due to manufacturing errors, aging, or damage, preventing it from tripping even when an overcurrent condition exists. Secondly, incorrect rating. If the OCPD is not properly rated for the circuit it is protecting, it may not trip at the appropriate current level. For example, using a 30 amp breaker on a circuit that should have a 15 amp breaker could allow excessive current to flow before the breaker trips. Thirdly, nuisance tripping. Frequent nuisance tripping can lead to the use of oversized breakers which can protect against unwanted trips but may fail to protect against dangerous overcurrent conditions. Fourthly, high impedance faults. High impedance faults such as those caused by loose connections or damaged insulation may not draw enough current to trip the OCPD, even though they can generate significant heat and pose a fire risk. Fifthly, environmental factors. Environmental conditions such as high temperature or humidity can affect the performance of OCPDs, potentially causing them to malfunction or trip improperly. Sixthly, improper installation. Incorrect installation of OCPDs, such as loose connections or improper wiring, can prevent them from functioning correctly. Seventhly, lack of maintenance. OCPDs should be periodically inspected and tested to ensure they are functioning properly. Lack of maintenance can lead to undetected faults and failures. To prevent OCPD failures, it is essential to firstly, use high-quality OCPDs from reputable manufacturers. Secondly, ensure that OCPDs are properly rated for the circuits they protect. Thirdly, avoid oversizing OCPDs to prevent nuisance tripping. Fourthly, address high-impedance faults promptly by inspecting and repairing loose connections and damaged insulation. Fifthly, protect OCPDs from adverse environmental conditions. Sixthly, ensure OCPDs are installed correctly according to applicable codes and standards. Seventhly, implement a regular maintenance program to inspect and test OCPDs. Ensuring that OCPDs function correctly is critical for protecting electrical systems and preventing fires and other hazards. The National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety. Several articles and sections of the NEC address issues related to connections, overcurrent protection, and fire safety. These include firstly, NEC Section 110.3. This section covers the examination, identification, installation, and use of equipment. It requires that electrical equipment be installed and used in accordance with the instructions included in the listing or labeling. Secondly, NEC Section 110.14. This section addresses electrical connections, requiring that connections be made so that the conductors are electrically and mechanically sound. It also provides guidelines for torquing connections to ensure they are properly tightened. Thirdly, NEC Section 240.4. This section covers the protection of conductors against overcurrent. It specifies the requirements for selecting overcurrent protection devices, such as circuit breakers and fuses, to protect conductors from overload and short-circuit conditions. Fourthly, NEC Section 250.8. This section addresses the connection of grounding and bonding equipment. It requires that grounding and bonding connections be made in a manner that ensures a low impedance path for fault current to facilitate the operation of overcurrent protection devices. Fifthly, NEC Section 310.16. This section provides ampacity tables for conductors, specifying the maximum current carrying capacity of conductors based on their size, insulation type, and insulation conditions. Sixthly, NEC Section 406.4. This section covers receptacles, cord connectors, and attachment plugs. It requires that receptacles be securely mounted and that connections to receptacles be made in a manner that ensures a reliable electrical connection. Seventhly, NEC Section 408.55. This section covers the overcurrent protection requirements for panel boards. It requires that panel boards be protected by overcurrent protection devices that are properly sized and rated for the connected loads. Eighthly, NEC Section 590.6. This section addresses temporary wiring. It requires that temporary wiring be installed in a safe manner and that connections be made so that they are electrically and mechanically sound. These sections of the NEC provide guidance on making safe and reliable electrical connections, selecting appropriate overcurrent protection devices, and ensuring that electrical systems are installed and maintained in a manner that minimizes the risk of fire and electrical hazards. Proper crimping is essential for creating reliable and safe electrical connections. There are several steps to ensure a proper crimp. Firstly, select the right connector. Choose a connector that is appropriate for the size and type of wire being used. The connector should be listed and labeled for the intended application. Secondly, strip the wire. Use a wire stripper to remove the insulation from the end of the wire. Be careful not to nick or damage the conductor. The length of the stripped wire should match the recommended length for the connector. Thirdly, insert the wire. Insert the stripped wire into the connector until it is fully seated. Make sure that all strands of the wire are inside the connector. Fourthly, use the right crimping tool. Use a crimping tool that is designed for the specific type of connector being used. The crimping tool should be in good condition and properly calibrated. Fifthly, position the tool. Position the crimping tool over the connector according to the manufacturer's instructions. Make sure that the connector is properly aligned with the crimping dies. Sixthly, crimp the connector. Apply firm, steady pressure to the crimping tool until the connector is fully crimped. The crimp should be tight and secure. Seventhly, inspect the crimp. Inspect the crimp to make sure that it is properly formed and that the connector is securely attached to the wire. There should be no loose strands of wire or gaps between the connector and the insulation. Eighthly, pull test. Perform a pull test to verify that the connection is strong and reliable. Gently pull on the wire to make sure that it does not come loose from the connector. Ninthly, insulate. If the connector is not insulated, apply insulation to the connection using heat shrink tubing or electrical tape. This will protect the connection from moisture and corrosion. Tenthly, document. Document the crimping process, including the type of connector used, the size of wire, the type of crimping tool, and the date of the crimp. This will help to ensure that future connections are made correctly. By following these steps, electricians can create crimped connections that are safe, reliable, and long-lasting. The Buchanan crimp, also known as a C-tap connector, is a type of electrical connector commonly used to make tap connections on solid or stranded conductors. The Buchanan crimp is designed to provide a secure and reliable connection without the need for soldering or other specialized tools. The Buchanan crimp is typically used in residential, commercial, and industrial wiring applications, such as making branch circuit connections, splicing wires, and terminating conductors in electrical panels and junction boxes. The Buchanan crimp consists of a metal sleeve or barrel with internal teeth or serrations that grip the conductors when crimped. The Buchanan crimp is available in various sizes to accommodate different wire gauges and conductor types. To install a Buchanan crimp, the conductors are inserted into the connector, and then a crimping tool is used to compress the metal sleeve around the conductors. The crimping process creates a tight mechanical and electrical connection between the conductors. The crimping tool is designed to provide a consistent and uniform crimp, ensuring that the connection is secure and reliable. When using a Buchanan crimp, it is important to select the correct size connector for the conductors being used. The connector should be sized according to the wire gauge and conductor type to ensure a proper fit and secure connection. It is also important to use the correct crimping tool for the Buchanan crimp being used. The crimping tool should be designed to provide the correct crimping force and profile, ensuring that the connection is properly crimped. After crimping the Buchanan crimp, it is important to inspect the connection to ensure that it is secure and reliable. The connection should be free from loose strands, sharp edges, and other defects that could compromise the integrity of the connection. If the connection is not properly crimped, it should be removed and replaced with a new connector. When properly installed, the Buchanan crimp provides a secure and reliable electrical connection that is resistant to vibration, corrosion, and other environmental factors. The Buchanan crimp is a popular choice for electrical connections because it is easy to install, cost-effective, and provides a long-lasting connection. Other alternatives include wire connectors, also referred to as wire nuts, and terminal blocks. Wire connectors are insulating caps that thread onto the ends of twisted wires to create a secure connection. Terminal blocks are modular connectors that allow for easy connection and disconnection of wires, often used in control panels and electronic devices. Each method has its advantages and disadvantages depending on the application, environment, and specific requirements of the electrical system.